Hi, my name is Hong Tu. I'm a fourth-year PhD student here in CPAS. My research focuses on high-frequency, high-power density DC-DC converter, modeling of magnetic components, and tunable electric components. Today, I will talk about Series-Resonator buck converter. It is designed for a two-stage solution for data center and automotive, 48 volts power distribution system. This work is sponsored by Texas Instruments.
48 volts power delivery system is increasingly popular and widely adopted in different applications, including data center, robot, vehicle, communication, and enterprise infrastructures. Take data center as an example. Power comes from the transmission line and it is delivered into each cabinet in the server halls. The 48 volts power system is housed at the board level. There are multiple voltage regulators, step-down voltage to power CPU, GPU, and all other loads. Compared with a conventional 12-volt system, 48-volt system reduces power distribution loss, conductor size, and weight and cost. This page compares different architectures for 48-volt system. Solution number 1 is to adopt a one-stage regulated DC-DC converter. It requires an ultra-small voltage gain less than 0.02. Normally, a transformer or coupled inductor is needed. They are hard to design and incur larger costs. Solution number 2 is to combine an unregulated converter with a regulated one. There is an extra unregulated intermediate bus voltage. The system efficiency is normally limited by the second stage efficiency. New solution presented here is a two-regulated stage solution. The first stage converter converts bus voltage into a semi-regulated intermediate bus voltage. With a regulated smaller bus voltage, the second stage will utilize smaller voltage rating switches and boost the second stage efficiency. The new Series-Resonator buck converter is designed for the semi-regulated first stage converter. It steps down voltage from 48 volts.
Shown here is a prototype of the Series-Resonator buck converter. It includes 4 GaN FETs in the middle. There's a 150 nanohenry inductor at the left-hand side. It handles 40 amps peak-to-peak current at full load conditions. There are 2 1.2 nanohenry output inductors at the top side. The current ripples are about 2 amps. The resonant capacitor and series capacitor are at the back side. The prototype is now running at 2.6 MHz at 48 volts input voltage, 7 volts output voltage. The first 2 waveforms of the top are the drain source voltage of the switch A1 and B1. Looking at the first waveform, before the turn-on of the SA1, the parallel resonant tank resonates with the SA1 output capacitor. The circulating energy stored in a resonant tank discharging the capacitor. As a result, SA1 is turned on at 0 voltage. It is similar for the switch B1. The other 2 waveforms at the bottom half are the drain source voltage of the switch A2 and B2. Those 2 switches function as synchronized rectifiers. Looking at the third waveform, the voltage of switch A2 drops below 0 before turning on. It shows a good ZVS turn on. At the end of the on period, the SA2 voltage climbs up smoothly after the switches are turned off. This indicates a very small turn-off current. SA2 is turned off at 0 current. It is similar for the switch B2. A Series-Resonator buck converter is realized by adding a parallel resonant tank next to the series capacitor. The resonant tank reduces all switches' voltage to 0 at turn on and all low-side switches' current to 0 before turn off. A 2 MHz prototype with a peak efficiency of 98.5% was built to demonstrate the viability of the topologies. While the results confirms the viability of the new topologies, mass analysis, optimization, and design trade-offs are among the issues to be reported in the near future. Thank you for watching this video. If you are looking for more details, please check out our publications in IEEE. We appreciate your interest in CPAS student research.